Hello guys, good morning. What happened to the rest? Shh. What happened to the rest of you? Hello guys. Are they all what? Are they all affected by the coronavirus or some? Yeah. Anyway, okay, let's begin, guys. This is the Math Society annual ball. So if you want to go there, just scan this, right? If you want, I mean, it's an annual event held by the Math Society in the math department. Okay, guys. The next thing, okay, I'll put it over here. If you want to scan it. The next thing I want to talk about is quiz 5. I'm really disappointed with the performance. I mean, a lot of people got full mark, but also a lot of people did not get the full mark. And I want to talk about it, if you don't mind, okay? The first thing is that about 80 of students did not hand in quiz 5, which I find very disappointing, because I told you that if you have any doubts or if you don't know where to start, you can email me 24/7 or Zoom me 24/7. So if you have no clue about what to do, you can just Zoom me or email me or see me in person. I'm in Alan Turing Monday to Friday until 6 p.m. And I'm also happy to see you during the weekends, Saturday, Sunday, all right? And the next thing is, all right, about doing quiz 7, the question was to show that k hat, which is the minimum, can you listen, please? The question was to show that this is a biased estimator for k, right? So the first thing you need to do, I think I did similar questions to this in the lectures. So the first thing you need to do is to find the distribution of this. So let's say let z or z equal to the minimum, all right? And to find the distribution of z, you need to first find the CDF, right? And the CDF of z can be shown to be equal to the following. I'm not going to go through the derivation. You can see the website for the full solutions, but the CDF is something like the following. All right, this is the CDF, right? Now, the next step is to find the density function, which is hello guys, please could you listen? It's the derivative of the CDF. And a lot of people had difficulties. I find this amazing because you've done one full semester of calculus, and yet you don't know how to a lot of people had problems differentiating this with respect to z, which I cannot understand, because I'm not here to teach you calculus. I'm here to teach you statistics, right? I mean, if you don't know how to differentiate, I'm sorry, I cannot do anything much about it. Okay. Now, what's the derivative of this with respect to z? I mean, a lot of people couldn't find the correct derivative of this. I can tell you that. I mean, the correct derivative is this. You should differentiate. I'm not going to show you how to do it because you should know. You should know how to find the. You should know how to find the derivative of this with respect to z, given the courses you have taken, right? Okay. So this is the correct derivative of this, right? And many of you, many of the 360 students in this class could not find the correct derivative, right? All right, and then the bias. The bias is, of course, is defined as the expectation minus the parameter. Now, to find the expectation, you just integrate z times the PDF, which is right. So you say z times the PDF integrated over z. Now, once again, several of you had problems doing the integration, right? Once again, integration is not something I can teach you because it's something you should know how to do, right? Okay, and also some of you had problems finding the limits of integration. The limits of integration should be from k to infinity, because if you look at the question, if you read quiz 5, it says explicitly that x must be greater than k. So in other words, the lower limit must be k, the upper limit must be infinity, right? I mean, if you read the, it says explicitly in quiz 5, in the question of quiz 5, that the lower limit must be k, and the upper limit is infinity. So the integral must be from k to infinity, right? Not, some people put that as 0 to k, some other people put it as 0 to infinity, right? The finding the limits is really important. I mean, you should read the question very carefully before actually finding out what the limits of integration are. Okay? Anyway, those are my comments. These are my comments on quiz number 5. And for one more comment is for quiz 6. Right? For doing quiz 6, which is due next Tuesday, you can assume the results of quiz 5 without actually having to prove it again. Okay? So there's no need to repeat quiz 5 again. Okay? Is that clear, guys? Yes. Okay. Now let me return to what we did on Tuesday. On Tuesday this week, I talked about the one method for constructing point estimators. And this method is known as the method of maximum likelihood, right? So there are basically 4 steps. There are 4 steps in the method. The first step is to calculate something known as the likelihood function, which, if you have continuous data, is just a product. Is it coronavirus? Not yet. It's just the product of the density function over the n data points, okay? That's the first step. The second step is to take the log of the likelihood, which is the log of this, so it becomes the sum of the logs, right? And the third step is to differentiate the log likelihood with respect to the parameter theta and set that to 0 and solve this equation, which I call star, right, for theta. And the final step is, if theta hat is the solution of star, And if it does satisfy this, that is the second derivative at theta hat is less than 0, then theta hat will be the MLE for theta. MLE here stands for maximum likelihood estimated, right? So this is the most popular in statistics. This is the most popular method for constructing point estimators, right? So this is for continuous data, and this is for discrete data. It's the same thing for discrete data. So the only differences are with the likelihood being the product of the PMF, not the density function, right? And also this is the log likelihood is the sum of the log of the PMFs, okay? So those are the only differences when you have discrete data, right? Then I did 4 examples. Sorry, I did 2 examples on Tuesday. So this is this is example 1 I did on Tuesday, and this is example 2 I did on Tuesday. Now I gave you an example 3, and I asked you to do it. Did you guys, had you done this, guys, or not? Some of you sleeping. Come on, it's 11 o'clock. It's not sleeping time. All right. So the first thing you need to do is to write down the likelihood function. All right, what's the likelihood function? What's the density of this, guys? All right, this, I'm sure all of you know the normal density of the normal distribution with parameter theta. Mean, theta is the mean, and variance equal to 1. Okay. So let's see if we can simplify this. So this will be all right, so this is the simplified form of the likelihood function. Step number 2 is to take the log of the likelihood. So it's the log of this, so it is going to be minus right, this is the log likelihood, right? Step number 3 is to take the derivative of the log likelihood with respect to theta. So this is a constant, so the derivative of this is a constant, so it's 0, minus the derivative of this. I mean, as I said already, I found a lot of weakness in your calculus. Not all of you, but many of you are weak in calculus, and you really need to improve. You really need to improve your calculus if you want to do well in this course, right? Okay, so this is the derivative of this one, okay? And if you simplify the 2 and the 2 cancels, minus and minus cancels, so this becomes this, right? So this is sum of xi minus the sum of theta. Okay, so this is, it's all in brackets like this. So this is sum of xi minus n theta, and set this to 0. Okay. Now if you solve this equation, clearly that I'm going to call it the solution, I will call it theta hat, because remember, you should go back to the first lecture that we had for this course. Anything that an estimate of a parameter, you need to put a hat on top, right? So whenever I put a hat on top, it means it's an estimator of theta, right? And it involves, and it's a function of the data. So in this case, yes, and this is the sample mean. Okay, guys, are you with me? All right. Now that's only step number 3. Now we're not done yet. Step number 4. We need to find the. Can you guys stop talking, please? The second order derivative of theta, of the log likelihood with respect to theta, is going to be minus n, which is negative. Hence, okay, are you guys with me? All right. So you need to show the last step, step number 4, is to show that the second order derivative of the log likelihood is a negative number. In this case, it is so, right? All right. All right. Now, example 4. I mean, the reason I am doing so many examples is just to bring you confidence. You know, when I give you quizzes, I expect you to do them because I've done so many examples. If you can go through all these examples, you should have little difficulties doing the quizzes, right? Okay. Right. So here we have a random sample from a normal distribution with 0 mean and variance equal to sigma theta squared, and we want to find the MLE of theta squared. So the first step is to write down the likelihood of theta, which is the product Yeah? You're right. So the mean is 0, the variance is sigma theta squared. So if you simplify this, you get this, okay? So this is the simplified form of the likelihood function, right? The next step is to take the log likelihood right? This is the, can you guys listen please? This is the log likelihood, right? And the next step is to take the derivative of the log likelihood, which is going to be minus n over theta and plus 1 over theta cube. All right, set this to 0. All right, so solving this equation for theta, you get theta squared. Once again, you need to put a hat, right? Remember, every time you write an estimator, you need to put a hat on top of the symbol, right? So this becomes 1 over n all right, so this is the estimator for theta squared. Now to find, okay, let me put this over here. Now we need to show that the second derivative is negative, right? So that's step 4. So the second order derivative is the first order derivative of the thing on the right hand side. So that's going to be n over theta squared minus 3 over theta power 4 times sum of xi squared. Right, now we need to show that this guy is negative, right? Now the best way to do this is as follows. I'm going to pull out 1 over theta squared outside, and okay, and now at this step I'm gonna replace theta by theta hat, right? So this becomes right. Okay, now we know that theta squared hat is equal to this guy here is equal to 1 over n times the sum of xi squared. Okay, you see what I'm doing? I'm just replacing theta squared hat by the solution that we got. Now this guy here and this guy here cancel, so you get which is negative. You follow me? Yeah? Okay, so hence all right, guys. Is there any questions on this, guys? So here, sometimes doing the last step, the step number 4 can be tricky, right? So you have to be careful. So you need to show, like in this case, it's not straightforward to do the last step. So you need to do some working to show that the second order derivative is less than 0, right? You follow me? Any questions? Yeah. So that's example 4. All right. The next one, I want to do example 5. Yeah, did I do this exam? I don't think I did this before. Anyway, so here the question is that you have a single data point x, which has a binomial distribution with parameters m and p, right? And we want to find the MLE of p, right? So in this case, the likelihood function for p, because you only have one data point, right? The sample size is 1. So in other words, n, remember, the sample size is like I from 1 to 1 of p x p. So, p this is the probability mass function. Maybe I should use some other symbol like theta maybe. Let me call this theta, just not to confuse. Okay. Let me call this theta. All right. So you only have one data point. So it goes from 1 to 1. Right. So this becomes m choose x p to the power x. Sorry, theta power x. 1 minus theta power m minus x. You follow me? I mean, this is something that a lot of people get confused with. When you have a single data point, the likelihood is the same as the density function. In this case, the probability mass function, right? All right. So second step is this should be theta again. Is to take the log. Okay, so that's the log of the likelihood. And the third step, this is step number 2. Differentiate this with respect to theta. So you get x by theta minus m minus x by 1 minus theta. Set this to 0. So this implies that and this implies that x times 1 minus theta is m minus x times theta. Now you should solve this, guys. You should solve this for theta. You get theta hat equal to x divided by m. You follow me? Yeah. So this is the solution for theta hat. Now, to show that this is a MLE, you need to find the second order derivative, which I'm going to do now. So part 4, the second order derivative with respect to theta, it's going to be minus x over theta squared minus m minus x over 1 minus theta squared. Yeah. Because x is positive, m minus x is positive, this is clearly less than 0, right? Okay. So hence p hat equal to what's that? X divided by m is an MLE of p. Sorry, I mean theta hat. Sorry, I'm confusing theta hat. MLE of theta. Okay, guys, are you okay with this? Any questions? Just feel free to talk to me, guys. It seems a lot of people are keeping away from the lectures. I don't know why. Maybe the coronavirus. I don't know. Yeah. I was also disappointed with the number of people who came yesterday for the tutorials. Can you please come to the tutorial? There are 2 tutorials this afternoon, and there's a tutorial tomorrow from 11 to 12 also. So please, if you haven't been to any of the tutorials so far, please do come to one of the 3, okay? It's really important, guys. This is example 5. Michael, can you keep, can you listen to me, the lectures, please, Michael? Example 6. Example 6 is a variation of example 5. Suppose you see the difference between this question, you see the difference between example 5 and example 6. There's a subtle difference. This is example 5, where you have just a single data point from a binomial distribution with parameters m and theta. Same as example 6. You find the MLE of theta, right? But here, not a single, but we have n IID data points from a binomial distribution with parameters m and theta, and find the MLE of theta. So the questions are different, they're not the same, right? Okay, so the first step is to write down right, this is the likelihood, right? That's because you have n data points, not just one. Remember there, here the likelihood is equal to this because you only had one data point, right? Okay? You see the difference, okay? So if you simplify this, you get okay, this is what you get. This can be simplified further as follows. All right, so this is the simplified form of the likelihood function, right? And the next step is to take the log of the likelihood. So step number 2, the log of the likelihood function, which is going to be the log of this. So it's going to be the sum. When you take, remember, when you take the log of the sum, log of the product, it becomes sum of the logs, right? These are formulas I showed you before. Right, and the log of this is going to be this. And the log of this guy here is going to be right. Okay, so this is the log likelihood, and the next step is to find the derivative with respect to theta. So d log now you should differentiate that with respect to theta, guys. This is what you will get. You will get all right. So this is the derivative with respect to theta. Set this to 0, right? Implies okay. Now solving this is not difficult, so I mean I will let you do the job because I'm not gonna. You should solve this equation for theta. This is what you will get. Okay. All right, guys. So that's step number 3, guys. Now step number 4 is to show that the second order derivative is negative, which is not difficult here because all you have to do is differentiate that one more time. And this is clearly less than 0 because sum of xi is positive, mn minus sum of xi is positive, so this must be negative, right? All right, so hence the conclusion is that all right, is an MLE of theta. You follow this or not? So you see the difference between this example and the previous example we did. In the previous example, we only had one data point. So the likelihood was same. The likelihood was same as the density function. But in this example, we have n data points. So the likelihood is the product of the density function. So you have to be careful about reading the question. So this is example 6. Now I'm going to do, I don't know whether we'll have the time, but I will start at least example 7. This is a tricky one. This is really, I will let you do this by yourself if I don't have the time. Suppose Right, here you have a random sample from a normal distribution with mean equal to theta and the variance equal to theta squared. And we want to find the MLE of theta, right? So, as I said, this is not straightforward. The first thing you need to do is to write down the likelihood function, which is what I am doing right now. Okay. Now, and then simplify this. You should simplify this. Yeah, this is what you get, okay? That's step number one. Step number two is to take the log likelihood. So all right. Okay, at this stage, you will be best advised to simplify this before you go further. So that's what I'm going to do now. Because what you have is a quadratic polynomial here, so you can open the brackets, right? Okay, so I'm going to open the brackets now. So it's going to be now, if you open the brackets here, you will get three terms. The first term will be this, right? The second term will be this, and the third term will be this. You follow me? Yeah, it's just a plus b squared, okay? Now, I'm going to take the summation inside each of these three terms, right? So you get the following. You get this is the first term, right? For the second term, you get a plus because minus minus is a plus. And 2 theta will cancel. So you get 1 over theta times the sum of xi. Do you follow me? Yeah. The 2 theta will cancel with this. And for the third term, because you have minus plus, you get a minus. And this is n theta squared, so it will be minus n over 2. I mean, this is simple algebraic simplification. Do you see how I got from this to this? Yes? No? Yeah? You guys okay? Yeah? Okay. All right. So that's why they're here. And that's step number 2. Step number 3 is I'm gonna differentiate the log likelihood with respect to theta. So you differentiate that guy here, right? So you're gonna be minus n over theta. You guys okay? Yeah. And you differentiate the next term, you get plus 1 over theta cube sum xi squared. Differentiate the next term, you get minus 1 over theta squared sum of xi. Okay, and we're going to set this to 0, right? So the problem we have is we have to solve this equation, right? So let's see how we can do it. I know I'm running out of time. So this, to solve this equation, what I'm going to do is I'm going to multiply everything by theta cube, so you get minus n theta squared plus the sum of xi squared minus theta equal to 0. And this is the same as n theta squared minus plus equal to 0. Now, does this ring a bell to you guys? Have you seen equations like this before? Yes or no? Have you seen something like you should have a theta squared plus b theta plus c equal to 0, then implies this is minus, you remember the formula? What's the formula for this? Minus b plus or minus b squared minus 4ac divided by 2a. So I'm going to stop here, but before I see you next time, I would like you to solve this equation and show that the second derivative is negative, right? So can you do this before I see you on on Tuesday next week? And once again, please do come to the tutorials. There are 2 tutorials this afternoon and 1 tomorrow at 11. There are no coronaviruses in the rooms. Yeah, 1 to 2. 1 to 2 I'll be there. But tomorrow you have 11 to 12 tomorrow. Okay. Okay. You mean here? Okay, thank you, man. Have a good day.
Yes. When you differentiate from here to here, you've still got the minus. Shouldn't this be a plus?
No, it's still a minus because you have minus, so it's still a minus.
Oh, okay.
Yes, thank you, ma'am. Thank you, guys. Thank you, guys. Thank you, Paddy. You too, man. Don't get the coronavirus yet.
No, my bad. No, I just got confused.
No, it's still minus because you have to take this to -1 and a minus here. So it's still a minus, sir. Hello, how are you? Hello, how are you?
I realize a lot of people submit like the homeworks like really like for me,
Not-
I know.
Not everybody, yeah, some people.
For me, like I always submit like always submit.
Thank you. Have a good day. Yeah. You submit early all the time.
No, I submit it on one day.
Okay.
That's not early. That's not early. It's like one day.
Yeah, that's okay.
I think it's because like I do all of my stuff like over the weekends.
Yeah. Yeah, it's okay. I'm surprised how many people have problems with calculus. They don't know how to differentiate, don't know how to integrate. Terrible. Terrible problem. I don't know what to do.